Hi, everybody. We're starting section 2.11, the first part of which is implicit differentiation. Now, first, I'm going to just give you a little bit of motivation of why this is so awesome and important and why it's so necessary and how great it is. That's the first thing I'm going to do. And then the second thing I'm going to do is the main thing is really just work out a whole bunch of problems and show you how this implicit differentiation actually works. So let me just share my screen with you, and we're going to start with the motivation. So the motivation is as follows. So here's implicit differentiation. Now the next thing is related rates. That's going to be later on in this section, but we're going to start with implicit differentiation. So if you have a function that you have to differentiate, usually it's given explicitly as a function of like y is explicitly a function of x. So y is equal to x squared plus e to the x. That's called explicit function. I could separate y, and I'd separate y on this side of the equation, and then just all x's on this side of the equation. And sometimes I can have something like this: y to the third minus 3x squared plus 5 equals 5. And I could bring the x squared over to the other side. I could then take the cube root to get rid of the y cubed, and I get y equals the cube root of this, which also is an explicit, it's an explicit function. It's a pain. You have all these radicals and chain, whatever, but you can do it. It's not the end of the world. You could definitely do it. But sometimes, and this is really where we need implicit differentiation, sometimes you're going to have something like this: y plus e to the y equals x squared. And like, there's no way you're going to do this. How are you going to solve for y? If you bring e to the y over to the other side, you still have y is equal to something. You have to have just a y alone on this side and only x's on the other side. But what am I going to do to e to the y? If I take the log, I could take the ln to get rid of the e, but then I still have the ln y. It's a big mess. So there ain't no way we's ever gonna solve this, explicitly for y. So what we're gonna do is we're gonna use implicit differentiation, and the key of implicit differentiation is that it's based on something we have to remember. It's based on chain rule because we're viewing y as a function, as an implicit function of x. So we're assuming that y is some kind of function of x, even if we can't solve it explicitly. That's why I say it's an implicit function. And then we differentiate and we use the chain rule. So let's switch tracks now. I want to go to my paper and pencil and just I want to work out a whole bunch of problems for you. So let me get to that right now. So I have to stop the share, and then I have. Here's a nice little problem. Find the slope of the tangent to the circle x squared plus y squared equals 25 at the point 3, 4. Now this is actually something which I could do I could do this without implicit differentiation. I could solve for y and get a big radical. It'd be a big pain, but I could do it. But instead, we're going to use implicit differentiation and watch how phenomenal. So I'm basically taking d dx of the whole equation, x squared plus y squared equals 25. So I'm going to take the derivative of everything. And that's going to give me the derivative of x squared is 2x. The derivative of y squared is 2y times the inner derivative. And I don't know what the inner derivative is exactly. I'm just going to call it y prime. Remember, we're viewing y as though it's some function of x. When I take a derivative of y squared, I'm using chain. I have to use the chain rule, the outer and the inner. So that's my outer right there. That's my inner right there. Okay, and that equals, now the derivative of 25 is 0. So now I want y prime, so I'm going to solve for y prime algebraically. I'm going to subtract 2x from each side. I get 2y prime equals negative 2x. And now I'm going to divide both sides by 2y. And I get y prime equals negative x over y. Now I'm going to look at the point. Now I'm going to go look at the point 3, 4. So y prime, watch how I'm writing this. Y prime of 3 comma 4. So I'm it's sort of like a funny kind of function notation. I'm writing y prime instead of writing y prime of 3. I'm writing y prime of 3 comma 4. Negative 4. And pow, that's my answer right there. And that was so super simple. So the slope, so let's just draw the picture here. I never drew the picture. Here's our circle. Radius of the circle is 5. We know that from algebra. And this point over here is 3 comma 4. Is that kind of over there? So the slope of the tangent, let me draw it. Slope of the tangent. Slope of this tangent is negative 3/4. And that, something that actually makes sense. One is going down. So worked out beautifully. That was a great example. Let's do another example. Now for my next example, I'm going to do the same example we just did, but I'm going to do it without implicit differentiation. So I'm going to find the slope of the tangent to the circle x squared plus y squared equals 25 at the point 3 comma 4, but I'm not going to use implicit differentiation. I'm going to use I guess I'll call the old-fashioned way of explicit differentiation. So we're still going to call it example 2A. And so we know that x squared plus y squared equals 25. That we know. And now I'm going to solve for y. So I'm going to subtract x squared from each side. And I get y squared equals 25 minus x squared. And then I'm going to square root each side. And y is equal to the square root of 25 minus x squared. Now, I'm good with just the positive because we're dealing with a positive y value here. We're dealing with the 0.3 with y is positive. So I'm going to stick with the positive square root, I'm fine. Now, to take the derivative here, to get y prime, well, first I have to rewrite this. This is equal to 25 minus x squared to the 1/2 power. So y prime is equal to 1/2 25 minus x squared to the negative 1/2 power, because 1/2 minus 1 equals negative 1/2, times the inner derivative, which is negative 2x. So again, that's the outer, and that's the inner of my triangle. And this is a little bit of a thing. Let's clean this up a little bit. Y prime is equal to, let's see, negative 2x over 2 radical 25 minus x squared. That's what this is. The 2's cancel. So we have negative x over, now by the way, I'm going to just negative x over the square root of. By the way, spoiler alert, you can see right away that this is the same answer we got before, because before we got negative x over y. Now we have negative x over this radical, but this radical was equal to y. So really, we can see already we're getting the same answer. But let's just try to. There's no y's here, so let's say y prime of 3. And that is equal to negative 3 over the square root of 25 minus 9, which is negative 3 over the square root of 16, which is negative 3 over 4. So y prime negative 3. exactly the same answer we got previously. So yes, this could have been done without implicit and done explicitly. That's all because I was able to solve for y. It's not always possible. Let's. I'm going to do one more example on this video right here. I want to do the problem that we said before was impossible to do explicitly. So here's what we're going to do. We're going to take the derivative of both sides. So the derivative of y is just y prime. What is y prime? I don't know. We're going to solve it. The derivative of e to the y is going to be and derivative of x squared is 2x. Now, what I need to do is a little bit of algebra, not a lot, just a little. I'm going to rewrite y prime as 1 times y prime. Then I'm going to factor out the y prime. So I'm going to have 1 plus e to the y times y prime equals 2x. Now, I'm running out of room, so I'm going to rewrite this up here. 1 plus e to the y times y prime equals 2x. All I did is I just rewrote that up here. And now I'm going to divide both sides by 1 plus e to the y. And that all cancels. My final answer is y prime equals 2x over 1 plus e to the y power. And that is how we do it. Okay, everybody. That was loads of fun, and we'll see you guys all next time. Bye.